Right, let's go through the Kirchhoff's laws problems that we looked at today because they're a bit tricky. Kirchhoff's law, certainly the second law, the voltage law, is takes a bit of practice. So, as we know, the Kirchhoff's voltage law is that the total sum of the EMF gains is equal to the total sum of the potential difference drops around any closed loop. But as we know, if we have parallel circuits, we can have a number of closed loops. So this is where it gets a little bit tricky. If you have a look at the textbook, which I hope you regularly are after each lesson, you'll see that Kirchhoff's voltage law actually has an equation, which is useful rather than remembering the full text. And the equation is sigma, which we know for maths is sum, so the sum of. Now the symbol for EMF in physics is a curly E, like that. Okay, curly E, I think it might be epsilon, Greek letter. Now that's equal to the sum of the potential difference drops around the closed loop. Now we can replace V with IR for each resistance in the closed loop. So this becomes the sum of the IRs, where I is the current through each individual resistance in the closed loop. Okay, so that's much more useful to remember, I think. Right, so let's have a little look. We first looked at this question, which we actually finished off by doing it a simple way. Let's do this first. Okay, so right, if we were to work out the total effective resistance of these four, if we were to replace those four resistors with a single resistor, this is the value it would be. Right, 8 and the 2, we can replace those with a 12. So then we've got a 12 and a 12 in parallel. Now to work out the effective resistance of those three, we've got a 12 and a 12 in parallel is 2 over 12. Obviously we need to flip it. So these three have a resistance of 12 over 2, which is 6 ohms. Okay. We also have a 6 ohm in series with this 6 ohm. So the total effective resistance is 6 and 6, 12 ohms. Okay. Now, if we've got a 12 ohm resistor with a 12 volt power supply, okay, and if we remember V equals IR, or I is V over R. So IT, okay, because we calculated RT, the IT is 12 over 12, which is 1 amp. Okay, so that current there is 1 amp. Now because we have 12 volts and 12 ohms and 12 ohms, that 1 amp is going to split equally. So I1 is half an amp, I2 is half an amp. Okay, right, how to solve this using Kirchhoff's laws? Right, this is where we got a little bit stuck today. So the current law, quite straightforward. This is going to give us our first simultaneous equation. So the current law obviously tells us that IT is equal to I1 plus I2. Easy peasy. Right, now, what about the voltage law? There's actually two closed loops we're going to look at. Okay, there is closed loop number 1, and there is closed loop number 2. Right, closed loop number 1, let's do the first one. Right, the EMF gain, the total EMF gain is 12 volts. Now that's equal to, right, we've got in loop 1, we've got a potential difference across that resistor. We've got a potential difference across R2, that resistor, and we've got a potential difference across R3. So we've got 3 potential difference drops we need to add together. So the first one Okay, we're not going to use V, not going to use voltages, we're going to use IRs, aren't we? So the first one across R1, it's IR, which is 6, which is the resistance, IT, which is the current. Okay, so that's for R1. For R2, we've got I1 passing through it, but it's 8 ohms, so we've got 8 I1. Okay, and for R3, we've got 4 ohms, and the current again is I1. Okay, so this is just for loop 1. This is just for the first loop here. Okay, we can tidy this up a little bit. 12 equals, so we've got 6 IT plus 12 I1. Okay, so there's loop number 1. Now what about loop number 2? Now loop number 2 only has R1 and R4 in it. Okay, but it does again have an EMF of 12 volts. So that the total EMF is 12 volts. Okay, so that's equal to the potential drop across R1 plus the potential drop across R4. So 12 equals 6 IT plus 12 I2. Okay? Right. Now what I'm going to do is, this is how I solved it. So we've got 2 simultaneous equations here. Or we've got 3 simultaneous equations. We have this. We have this. And we have this. Right, a bit tricky this, because depending on which way you go, you can end up with 12 equals 12, or I2 equals I2, which is not really useful, is it? But there is a way of solving it, and that is to, okay, let's take the top one. Let's take the top one and make I1 the subject. So I1 is equal to IT minus I2. Okay? Now what I'm going to do here, I'm going to replace this fella with IT minus I2. Yeah? So this becomes 12 equals 6 IT plus 12 IT minus I2. Okay? Which becomes 12 equals 18 IT minus 12 I2. Okay? Now, what about this equation here and this equation here? Okay? I'm going to add that equation there to that equation there. Okay? If I add those 2 equations together, we get 12 by 12 is 24. 6 IT plus 18 IT is 24 IT. 12 I2 minus 12 I2 is 0. So this leaves us with remarkable scenes, an IT of 1 amp. Boom. Okay, yeah, took a few goes at that, but we got there. Okay, right, so that is that one there, and then you can substitute back in to the equations above, and you can get an I1 of 0.5 amps and an IT of 0.5 amps. So, a bit trickier than I first expected. Anyway, this is the really tricky one. So I'm going to just get you started. I'm going to give you the full solution here. I'm just going to get you started. Now, the eagle-eyed amongst you will notice that there's actually two batteries. Okay, two batteries in parallel with each other. What on earth do we do here? Okay, right. Well, firstly, not panic. But I'll show you what to do. Right, current one first. The current law. It's fairly straightforward. The diagram really helps us here. I think we're looking at I1 plus I2 equals I3. Yeah, so it's looking like this battery is pushing current that way. This battery is pushing current that way. Okay. And then I1 plus I2 is I3. Right. Let's work this through. The voltage law. Let's. How many closed loops have we got? That's the first good question. How many closed loops? Well, we have a closed loop here. We have a closed loop here, but we also have a closed loop here. That's the one. We've got two batteries in it. So, how are we going to solve this? Right. Let's look at the first closed loop. So the first closed loop, this one here. Right, EMF gain, we've got 6 volts from the battery. Okay. Now plus the potential difference drop across that and the potential difference drop across that. Now be careful here. We need to pay attention what current is flowing through each resistor. They're actually different, aren't they? We've got I3 through the 30 ohm and we've got I1 through the 10 ohm. So that's important. So the potential difference drop across this fella is 30 I3. 30 I3. The potential difference across this fella here is 10 I1 plus 10 I1. Okay, so that's our first one. Okay. Next one, next closed loop. What do we have? This closed loop here. Right. EMF gain, we've got only 2 volts here. 2 volts equals, right, how many potential drops? Well, we've only got a potential drop across that one. So we've got 30 I3. Now, this is the one that's a bit interesting. This closed loop here, right. Now, EMF gain. We have 2 batteries that are going to supply an EMF, aren't they? However, what do you notice about the batteries? They're in opposite directions to each other, aren't they? They're both pushing in opposite directions, so the total sum of EMF gains in that purple loop is the difference between them. We don't add 6 to 2 because they're in opposite directions. If those 2 batteries were pushing in the same direction, we'd add 6 to 2, but because we've got them in opposite directions, we need to subtract. So the total EMF gain around that purple closed loop is 6 minus 2. Now that's equal to the potential difference drop. Now the only one that has a potential difference drop is that one there, okay, which is equal to 10 I1, okay. There you have it, 3 simultaneous equations. Plus that one there. Right, I'll leave that with you. I shall leave that with you to solve what's the value of I1 and I2 and I3. There's a little bit of a twist. See if you can figure it out. Thank you very much. Any questions, please get in touch. Thank you. Bye.